Okay, cool. Hello, everyone. Welcome back to the Autonomous Seminar after the summer break. So it's my very pleasure to introduce today's speaker, Linus, who is currently a postdoc at the University of Edinburgh, and he's going to present this new paper on einspaces. And yeah, thanks very much for coming here today, Linus, and please take it from here.
Thank you very much for having me. So I'll be presenting our work, which is entitled einspace. It's a new kind of neural architecture search space focused on expressivity, and it's with all of these lovely people from Edinburgh. So to start off with, neural architecture search is kind of split into these three main components. We have the search space, which defines all of the kind of potential architectures we can consider. The search strategy is the way that we explore this space, like a policy for what to go for next. And then the performance estimation strategy is how to score each individual candidate architecture. In this work, we will be specifically focused on the search space, but there's plenty of work in all the three components here. So zooming in a bit closer in search spaces here, there's plenty of different types of search spaces from the literature. Sort of early, more basic version is the kind of chain structure where you have multiple layers composed together in a kind of straightforward sequential way, where each layer has, or it can be a more complex operation, but there's a sort of predefined set of things that can go on each position here. And then we get cell-based, which takes this kind of step further. So it incorporates a kind of bias, which we see often in human design network, which is that we have repeated structures. And so instead of searching for everything all at once, we search for a cell, which contains multiple operations in different kind of branching ways, but then they are composed together or repeated to form the larger architecture. Then we got macro spaces, which also, in addition to searching for the kind of low-level operations, also searches the high-level structures. So the macro, so I've colored the arrows here to also indicate these are now also options that can be changed. And then we get hierarchical spaces, which kind of combines the cell-based with the macro. There's a few different versions of all of these things, but like one of the most canonical ways is you have both the kind of macro search, but also kind of a lower level, for example, a cell-based search at each location. So in this work, what we introduce fits best within the macro family, which means that we search both the kind of overall structure of the architecture, but also all of the individual components and low-level operations. So more of the motivation here is that we argue that if we have a narrow search space, we've seen for previous work that the search strategy that's used is or tends to not be as important. As an example, we have NAS Bench 201 here on the right-hand side, which is a very common search space, and it's very good in the sense that it's a tabular one, so you can look up the performances of all of the architectures quite easily. But we see that a lot of the architectures are clustered to the top of the performance range here. And so if you use a kind of basic random search policy and you sample 100 networks, you are likely to get one of the well-performing ones, perhaps not the best, but still be competitive. So some papers have found this and reported, like here, state-of-the-art NAS algorithms perform similarly to random search policy. Another thing with these narrow or smaller spaces is that they tend to be focused on you get kind of a standard architecture, like a residual network, and then all of the architecture within the search space are different variations of that type of architecture, so based only on kind of convolutional components and pooling and so on. So it's limited in a few ways. And this is the figure from this paper, which kind of shows how it's a cell-based search space, and the reason it's cell-based is partly to reduce the complexity of it, but this also means that we get these kind of problems with the small and narrow properties. For example, we have 5 options across 6 different edges or operations, and so we end up with about 15,000 architectures. So this is kind of on the lower end of the complexity of search spaces. And now we're going to run away to the very other end of the spectrum to very large search spaces, where it turns out that the search strategy is very important. So this specific search space is called AutoML0, and it is based on much more low-level components. So it's actually individual lines of code across 3 different functions here, the setup, predict, and learn functions. So all of these low-level lines of code can be switched in and tried in different ways, but this also means that it's a very, very expressive but very complex search space to search. And a line in this paper is that they find that evolution as a more clever search strategy is about 5 times more efficient than random search. So there's a big difference here in using something a bit more intelligent for searching this. So this is the lovely big figure from this paper, which shows how they start off with a complete empty algorithm. So all of the search there kind of starts from scratch with nothing. But as you search across, I think it's thousands of CPU hours, they find all of these nice things that humans have, of course, designed over the years. You get your linear models, and you get some specific learning rates, randomized or hard-coded learning rates. You get ReLU activations, you get random weight initializations, and so on, gradient norm. But at the end, you arrive with an algorithm which, it isn't kind of at the power level of modern neural net architectures. So they find nice things, and it kind of validates and confirms all of the things that humans have designed themselves. But it's hard to get further than that. So that means that it's a search space which is very big, but also very hard to search. That is a noise in my house here. I will very, very briefly check if it's something with a door. So I'll be back in a second. To the other. Thank you. So here we have kind of the 2 extremes. So we have NAS Bench 201, which is a kind of low expressivity, but it's quick to search and easy. And then AutoML0, high expressivity, but it is slow because of the kind of structure of the search space. So what do we want? We ideally would want a search space which is both expressive enough to contain diverse good architectures. And specifically, one of our goals is to design a search space which kind of goes beyond a single architectural family, like convolutions, but also not so huge that searching this space ends up being complex or super slow. So we have some work that has tackled this. We have, in particular, the construction of hierarchical search spaces based on context-free grammars paper here by Schröder et al., which they take a kind of formalism of context-free grammars to capture or encapsulate existing search spaces. So this is a hierarchical version of the NAS Bench 201 that we looked at before. So kind of the lower level of this context-free grammar here describes the NAS Bench 201, and the higher level there is kind of the macro hierarchical level to it. So kind of a top and a lower level here. And this is a space which is very big. It is, compared to the 15,000 before, we have about 10 to the 400. Compared to the number of atoms in the observable universe, it's rather big. It should be very, very hard to search, and we can't, of course, get through all of them. But it does turn out that with clever search, with a thing that they designed, the Bayesian optimization method with a hierarchical kernel, ends up performing really well here as well. So it turns out we can have a very big and expressive search space, which is also fairly efficient to search. But so we still see some limitations to this. So this hierarchical NAS bench, it is expressive, but it's still fairly fast to search. So it kind of ticks some of those boxes, but we still don't have a sort of single search space that unifies kind of different types of architectural families. Because if we want to use NAS to find some new architectures that are kind of truly novel or interesting, something that we haven't found before, then we need to go kind of beyond looking at some of the spaces that focus on like specific convnet style things. So this is one of the motivations that we have. We want to build upon this and build upon this kind of formalism of context-free grammars, but really create a unified search space based off of multiple architectural families. So how do we do this? So we want einspace to, like I said, be a space that unifies different architectural families, and we kind of limited the scope a bit here to consider specifically convolutional networks, transformers, and MLP-only networks, like exemplified by the MLP mixer. We want to build it similar to the previous work with context-free grammars, but also do it in such a way that it's kind of a minimally complex grammar that unifies these, because one kind of naive way would be to take existing search spaces for convnets, transformers, and MLP only separately, express them in the context-free grammar, and then kind of merge them together into one. But we kind of take a more bottom-up approach and try to do it in the kind of most general and least biased way, because we want to include architectures that not only sit within these kind of circles in the Venn diagram, but also things that go between them and go beyond them to make it a truly kind of diverse and expressive space where you can find novel things. So in order to create the space, we need to kind of discuss what are the fundamental operations that we're going to consider. So einspace is essentially centered around a single parameterized operation, which is the linear layer. So parameterized operation, I mean, any of the operations we have in architectures that kind of have a significant number of weights, biases in there. And all the other operations that we include are there to kind of enable a lot of the different functionality we see in these families. So branching structures, which means that we can, do skip connections by branching out and then merging back in again, and we can do multi-head attention and all of these things. And also functions that allow more complex parameterized operations like convolutions, which we will see. So these fundamental operations we use are categorized into 4 groups of functions. So we have the branching group, aggregation group, routing, and computation. And we will go through all the operations that are in each of these groups. So branching first. So you'll see the little yellow circle. Later on, as we will look at architectures, any operation within those architectures that are visualized, that are yellow, are inside of the branching group, and so on. So first function here is clone. So in general, all of these functions act on tensors. So the branching group, each function takes in a single tensor, and then will process it and spit out multiple tensors. So clone takes a single tensor and then basically copies it, clones it, and then passes multiple tensors out. Group dim is a function which groups or splits along a specific dimension, like in a grouped convolution. So you take a specific dimension like the channels, you split it into 2 or 4 or whatever number of tensors and pass them out. Then we have a bunch of aggregation functions, which then merge things back together into one tensor. So they take multiple tensors as input and single tensor output. So matrix multiplication, addition, and concatenation are the 3 ways that we can merge things. Routing is kind of a specific group here, which allows certain structures. So the im to call and call to im functions will specifically enable convolutions, because im to call takes, an image kind of shaped input, transforms it into a way that makes it, if we have an im to call function followed by a linear layer, followed by a call to im function, that is a convolution. And the different parameters inside the convolution, like kernel size and stride, exist inside of these im to call and call to im functions. So this kind of decomposing convolution into things that allow us to really focus on this linear layer as the core parameterized operation. Then we have permute, or like transpose functions that swap the axes of tensors. And finally, we have the computation group, which contains some things that we're very familiar with, like the linear layer, normalization layers, activation layers, and positional encoding. So there's a bit more complexity and a bit more sort of hyperparameters within some of these functions, but overall, these are all of the functions that are included in our search space. We will see how these are then constructed into more kind of macro structures in the next slide. So the different macro structures, we basically call them different modules. So we start off with the sequential module, which is a very simple composition of two functions, much like we have nn.sequential in PyTorch and so on. And then we have a branching module, which will always have a branching function, the yellow thing there, which splits things into multiple branches. Then each of those branches are further kind of derived and can contain multiple different modules or functions. But then finally, it's all merged together in the aggregation function in purple. And then we have the routing module, which defines how these kind of routing functions are used. So it always has a routing function in green first, then something complex in the middle. In this case, it turns out to just be a linear function, and then a routing function at the end. And then finally, for a specific reason, which we'll come to later, there's also a sort of trivial module, which we call the computation module, but it will always just contain a single computation function. But it will be useful, as we'll see. So here is now the full context-free grammar. So if you're not familiar with what context-free grammars are, it's a way of formalizing a particular language according to a set of rules. So this is very much used in programming languages like Python. Under the hood, there's essentially a context-free grammar that says what is a valid Python program and so on. This can also be applied to language, where we can have things like, we group words into nouns or verbs and so on, and there are certain structures depending on each language of what sentences are kind of allowed and so on. So this is the formalism that we use here, but instead of like language or programming languages, it's like the operations within an architecture that we are modeling. So the context-free grammar always starts with like a starting symbol, S, and any capital symbol, so the S, the M, the B, the A, and the R1, R2, and C, these are the non-terminal symbols, which means that whenever we reach one of those non-terminal symbols, we will kind of continue expanding it with one of the options on the right side of that rule. And any of the lowercase, clone, group dim, and all of those functions there, these are the terminal symbols, which means that whenever we reach one of them, our kind of derivation ends, and that is part of the final string that we get. So there are two lines at the top which describe the kind of macro structure, which includes the modules. So M followed by M as the first option on the first line is in fact the sequential module. And then we have the next option, BMA, that's the branching module. And then R1M, R2 is the routing module. Okay, and now we will look a little bit more at the extra kind of implementation details that we actually add. So this grammar does describe all of the kind of allowable things, but there are a few priors that we put in there that add a little bit more knowledge or expert knowledge into what we're allowed to generate. So this is specifically due to branching, so the branching modules. So whenever we have a branching module, like I said, we have branching function that splits it into a number of branches. The way we do this, we allow either 2 branches, 4 branches, or 8 branches. And if we happen to split it into 2 branches, we say that the left and the right branch are unique. They are basically derived separately, generated separately. They don't have to be the same. But if we have a branching factor of 4 or 8, we say that we only generate one of the branches and then that is repeated across. So basically on the left-hand side is the way that we would create a like a skip connection, because the 2 branches are different. On the right-hand side is how we create a multi-head attention where everything is the same, maybe 4 or 8 times. So now we will go through the process of actually sampling an architecture. So remember I said that in a context-free grammar, we always have the starting symbol. So any generation always starts with this symbol. And the rules we had meant that we can go to a few different kind of module options here. In this case, we happen to randomly choose this m followed by m, which is the sequential module. And as we continue deriving this or sampling this, we will always go with the leftmost symbol. So that left m becomes this BMA, branching module. Then we go to the B. That goes to an actual function. So this is the group dim, which splits a tensor along a particular axis. M goes to C, which goes to a linear layer. A goes to a concatenation as the aggregation function. Then the second M will be derived into a routing module. And this R1 goes to im2col, M goes to the linear, and the R2 goes to the call to im. Which together, this im2col, linear call to im, like I said, basically creates a convolution. So one problem that we actually have using this naively like this is that there are so many different options and the grammar is very flexible that there are many, many architectures that can be sampled, which ends up being invalid because, for example, we may split along an axis which doesn't have that, equal number of things. So we may end up with a linear layer that isn't sort of big enough to then do a convolution with a particular kernel size. And there's various problems with shapes that could end up happening. So during our sampling process and the implementation, what we do is that we basically keep track and infer the future shape as we sample each operation. And if anything at any time goes wrong, we basically backtrack a step, try something else, and then if it continues going wrong and we run out of options, we backtrack another step. But by doing this, by inferring the tensor shapes, we can ensure that anything that successfully is generated is a valid architecture. So if we start with an input tensor, which is similar to CFAR10 image, for example, this group dim will perhaps split the final axis there, 32, into two 16 tensors. The linear layer will increase the final dimension that is 64. Then finally we concatenate, and there's two branches of final dimension of 64, which means they're 128. And then finally we get to this convolution style thing here, which transforms it in a particular way into this tensor. And then the number of channels is essentially increased before it transforms it back into the image shape. So this is how we kind of keep track of the tensor shapes and ensure that any of the sample architectures are valid. And because we will later be looking at evolutionary search within this space, we will also now look at how we can mutate an architecture. So the way that we do it, actually, I'll briefly mention this tree that we see here is called the derivation tree. So this is all of the options, all of the choices that are made within the grammar to produce the architecture. All of the functions of the architecture are on the leaves at the bottom, but the full thing is the derivation tree. So what we do when we mutate is that we sample a node uniformly at random from this derivation tree. So that includes all the different nodes in the tree. Then we resample from that node downwards in its subtree. So a complete subtree can be resampled, or if we choose just a leaf node, then we just change that leaf node. But we follow the rules of the grammar within this as well. And then finally, because when we mutate a certain section of the tree, some of the tensor shapes and other properties can be changed. So we just validate everything again to check if this is an architecture that can be trained and if it fits within the GPU and so on, other constraints we may have. So how would this example be mutated? So we will randomly sample a node. In this case, we randomly choose that node, which contains a whole subtree. So when we resample that, we change it. It went from this kind of branching module thing to a sequential module, and the new operations at the bottom are linear and ReLU. Then we validate the architecture. Because I, contrived this example, it turns out that the outputs match very nicely, and we still have a valid architecture here. So that's how mutation happens. Now, because we will be sampling architectures here, we can actually end up with a problem. So if we look specifically at this line, that contains the rule that M goes to a few different options, but some of those options actually contain the symbol M again, which means that we can basically recursively end up choosing the same options. Like if a single M goes to the sequential module, the first option, MM, then we have now doubled the number of things that eventually need to be generated. And so we can actually end up in situations where we continue generating a single architecture like forever and never terminate because of this problem. So we essentially introduce probabilities. So each option at each line will have a probability associated with it. And the probabilities along a single line will all add up to 1. So we will continue focusing on this particular line that's highlighted. So the first probability here that M goes to MM, given that we're already at the symbol M, is stated there. So the first 3 options contain the symbol itself. These are recursive options, but the final option here, M goes to C, is not recursive. That will always just end up with a terminal symbol or one of the blue functions at the bottom. So that means that whenever we encounter an M and go to a C, we will not continue generating or recursing or anything. So that means that we can essentially control some of this problem with how much we will kind of recursively generate things by setting this probability. If we have a high probability of going to C, we may, we will have a higher probability of terminating, basically. So this is empirically looking at this. So the second column there looks at this specific probability of going to C, the computation group, ranging from 0.9, so 90%, down to 30%. And we can see that the number of terminal symbols, or also similarly the number of non-terminal symbols within the architecture trees here that are generated. So this is me generating maybe 2,000, 2,000 architectures and taking kind of the average, the mean number of terminal symbols equivalent to the number of functions, the median, and so on. And we can basically see that as we get a lower probability of this particular function, all of the other options are more likely, and therefore we keep recursing, and so we get much more complex and bigger architectures. So there's certainly a trade-off here between like wanting to have algorithms that terminate, but also having an algorithm or a sampling procedure which can generate complex architectures. And it turns out we can do this nicely analytically. If we put all of these probabilities from our context-free grammar into a matrix, and then we compute the spectral radius of that matrix, we get a number. And if this number is above 1, then there's a non-zero probability that we will recurse forever, and that's bad. If this value is less than 1, then we're basically guaranteed to always terminate and always have, we will have quicker generation of architectures, and we will always terminate and so on. So what we do is basically set the value in practice to the value which is just above this. So you can see in the legend, it says the line is at 0.31. We set the value to 0.32 in our code, which means that we get the kind of the maximum complexity in our architectures without having any of the problems of these infinite generation. So this is, I've kind of described how we create our search space, and now we'll move on to the evaluation. But if there's any question at this point, just to clarify things, happy to open it up for that. Okay, good. Yes, so we will move on to the evaluation of it. So one thing that we want to focus on is evaluating on a diverse set of data sets, because we have a search space which we design for expressivity. We want to include a lot of different types of architectures in here, and so we want to evaluate it on a bunch of different types of data sets across different domains to really kind of see if this is something that's beneficial. So we have 2 broad benchmark suites we use. One is the NAS Bench 360, which contains a bunch of data sets from even like fluid dynamics to astronomy and so on. And then Unseen NAS, which is, I think It's the main one that I will show the results for now, but it contains things from computer vision to audio data sets and some language-related ones as well. So it's a diverse set across several domains. Before we get into the actual results, I'll describe another thing here, actually, which is related to how we define our search strategies. But these three architectures that you can see here, the ResNet 18, the Vision Transformer, and the MLP Mixer, these are what they look like when visualized within our einspace. So the colors correspond to the colors that I described before with the different function groups. And then we have the architecture itself at the top and its derivation tree at the bottom. And there is a little complexity thing here where there are actually multiple derivation trees that can exist for a single architecture, because there may be multiple ways of actually going through the rules of the grammar to achieve the final leaf nodes in that particular order and structure. And that's something which I want to look at in the future, but haven't actually explored yet what effect a different kind of derivation tree representation has on things like mutation and the evolutionary search. So the search strategies that we focus on here is basic random search, because we saw before that this tends to be competitive in some other spaces. So in our big space, we'll have a look to see whether it performs well or if it's kind of way behind, as we saw in the AutoML 0. Then we have evolutionary search, which is our main workhorse here. And we have a few different versions. So the specific version of the algorithm we use is regularized evolution, so RE. And this version, the RE scratch, means that we search from an initial population of random architectures. So we completely sample, I think it's 100 architectures, and that forms the initial population for the algorithm. Then we also initialize this initial population with some of these architectures we can see here. So the ResNet 18 is sort of the baseline network that is recommended for some of the benchmark that we use. And so we try to basically perform our search with initial population set to ResNet 18s, because after all, we have years, maybe even decades by now, of human architecture development. And so we may as well use them. And one of the powers of our space, because it's so expressive, it means that we can actually represent lots of these existing architectures within the space. And so we can start off the search with them. Similarly, we do a search where we have a mix of different architecture types. So the ResNet, a wide ResNet version, the Vision Transformer, and MLP Mixer. So this kind of takes the power of kind of the bias from human design architectures, but also within the space and the evolutionary search. So here is a plot that shows the average rank on this Unseen NAS benchmark. So this is the average rank computed across 8 data sets, and we want a lower rank. So lower rank means a better performance here. And so we have the split between einspace, which is, or any algorithm that is applied on the einspace search space is in orange, but any algorithm applied on a different search space is in blue. So on the very left, we have just the baseline network, just the ResNet 18. And then we have a few competitor algorithms here, PCDots, DrNAS, and Unseen NAS. And then we have our main regularized evolution one. So we can see that the best performing one is not one of ours. It's the Unseen NAS, which is kind of a version of a one-shot search with some clever pruning in there. But our search that uses a seeded population with sort of decent enough architectures, we both see big improvements from the original like ResNet 18 network to the one that we have found during our search. We see big improvements there, but also they perform well across a wide variety of the data sets. And similarly with the mix of the architectures there. Then if we look at the very right-hand side, we have the more like random search baselines here. So the very right pillar there is random sampling, which is just taking a bunch of random architectures and reporting the mean But then we have 3 random search on 3 different search spaces, and we see that random search within einspace does not perform particularly well. We can get much better performances with our evolutionary things seeded with things. But interestingly enough, in terms of ranking, we don't see particularly good performances from the evolution when we just search from completely random architectures. And I think this is because the random architectures that are generated initially tends to be quite small. So it starts off with a very a population of simple architectures, and then eventually builds up the complexity of those architectures, but it doesn't quite reach the power level that's enough for some of the datasets, some of the more complex datasets. But an interesting thing, like I discussed before, random search can be competitive across other spaces. We look at the random search on darts, is the pillar with 4.06 is actually performing better than the other PC darts. They're the more clever algorithm on that. Whereas in our space, we see that we can get good improvements from this. So overall, we get good performances, but it's not necessarily, the best across the board. This is on NASbench 360, or on some of the data sets here, because we're still working on getting through some of the last data sets. But on some of these here, we find that we perform better than the competitor and similar to the expert, which is kind of a handcrafted human design expert architecture specifically for these data sets, which is an interesting thing that the NASbench 360 suite has. But then specifically on the Nina Pro dataset, we get a performance which we believe is probably about state of the art on it. And so we can get really great performances here as well. Because it's fun to see how these architectures look, we will have a look at some specific ones. So this is the nice flower architecture that's found on the ADNIST dataset, which is part of the Unseen NAS bench that we saw. This is an architecture that performs really well, but it has this crazy branching structure, which ends up looking like a nice flower. Looking closely at this, I believe some parts of this aren't that necessary, because some of these functions inside that we can't exactly see, but some of them are essentially identity functions. So I think it can be reduced to something a little bit simpler. But it performs really well and it's beautiful, so I'm happy with it. Then we have the language data set so this is one where I believe it has adjusted a ResNet 18, which is a sort of bigger, longer version of this. So it's first, during its evolution, when looking at all the different steps, it's clear that it sort of reduces the complexity, because it turns out that network had a few too many parameters or was maybe too deep for it. And so it makes it a little bit simpler, and then it adds this extra branching in the middle there to do a little bit more parallel computation. And then finally, this geoclassing dataset, some satellite imagery, where we again have some fun branching stuff, and it performs competitively there as well. And I think, yes, that is the final slide. If you want to have a play around with our little interactive visualizer tool that I've made with some HTML code, you can scan that thing and go to the project page, where you get links to the paper and so on as well. But yeah, thank you very much.